안녕하세요. Welcome back to Automatic Control Systems lecture. I am Professor Kalyana Veluvolu with the School of Electronics Engineering. In the last week, we discussed on Bode plots, we discussed on the basic rules of, we discussed on how to draw Bode plots for simple pole, simple zero, quadratic pole, quadratic zero, and also pole and zero at the origin. In this class, we're going to use those knowledge and then we're going to develop a simple procedure on how to draw Bode plots for complex transfer functions. So the main purpose will be to actually learn how do we draw Bode plots for quadratic poles. Since the quadratic poles are of our interest in automatic control systems, we're going to spend some time on how do we draw Bode plots to analyze the behavior of control systems. So this is week 14, part 1, the fourth part of frequency domain. So we're going to actually learn how to draw Bode plots in this lecture. So I would like to review what we have gone through in the last class. So in the last class, we have learned about basic plots for magnitude and phase plots for simple zero, for the zero at the origin. This is 1 by s power n. So if you have n poles at the origin, you're going to have minus 20 into n. So we're going to have 2. So if this n decides on number of poles at the origin. So if you have 2 poles, it's minus 40 dB, 3 poles, minus 60 dB, so on. The same way, if we have zeros at the origin, you're going to have 20 into n. 1 0, 20 dB, 2 zeros, plus 40 dB, and so on. Similarly, phase also has multiplication with n. So if we have multiple poles and multiple zeros at the origin, we're going to have the phase multiplied with n accordingly for the poles and zeros. Now, if you go for a simple pole and a simple zero, the magnitude plots are very simple. So it has 0 dB until the corner frequency. So you can also write 1 plus j omega by s term. So it depends on how we actually, on the pole location P1. So it depends on whether you take t or 1 by t, it doesn't matter. So this is 0 dB and this is the corner frequency. You can also write P1 minus 20 dB per decade. So for the 0, you'll have plus 20 dB. The other point is with the phase. If you're looking at the phase, for corner frequency, for example, is P1, you have to actually take 0.P1, 1 decade before the corner frequency and 1 decade after the corner frequency and draw this phase. The phase is going to be 0 from minus 90. This is also same. If you have one pole, you have 0 to minus 90. If you have two poles, it will be 0 to minus 180, two poles. So if you have multiple poles, it will increase accordingly. So the phase plots and the magnitude plots for simple pole and simple zero. Then the most important, quadratic pole. So the quadratic pole, if we actually rely on the quadratic pole, the main aspect of what we are looking is this eta. So this eta behavior is very important. This we know this is a damping ratio and this affects the behavior. So depending on eta, the quadratic pole Bode plot is, the quadratic pole Bode plot varies. The basic plot is 0 dB until the corner frequency omega n. You see this is the omega n. We have to write in the standard form and then identify the omega n, and then from the omega n we are going to actually draw the Bode plot. So it's 0 dB until the corner frequency, and from corner frequency is going to be minus 40 dB. This is for quadratic pole. Since you have two poles, so you can have minus 40 dB. Then coming to phase plot, one pole is very simple, 0 to minus 90. So you have two poles, so we have 0 to minus 180 degrees, very important, you have 0 to minus 180 degrees. That is what you can identify. And the most important aspect is with the damping. So once you know the damping, it actually decides on what is 20 log 1 by 2 eta. So taking this value, we need to correct the Bode plot. So if this value is greater than 0.7, 0.5, 0.6, you have a negative correction. If it's less than, if eta is less than 0.5, you can have a positive correction. So depending on the eta value, the correction varies. So this is another important aspect in the quadratic pole. The next, we will actually go through a simple procedure on how to draw Bode plots. This is the first example. So I would recommend the students to print a few Bode plot papers, because if you print the Bode plot papers, then we can draw together. So I am going to show you how to draw, and I am going to draw the Bode plots in this class. So I recommend the students to print a couple of Bode plots and then draw together with me. So first take this equation. So we have a nice transfer function here. So I have a nice transfer function here. We can see that you have 1, 0 and then 2 poles. So 1, 0 and 2 poles. Then it is 2 simple poles. First step, change it to standard form. The standard form is where we can actually write in the terms of corner frequency. So most important is I want to write 1 plus j omega by 2 plus 1 plus j omega by 10, because you have to write in the standard form of 1 plus j omega by z1 or 1 plus j omega by p1. So this is the standard form. So once we can actually keep in the standard form, it becomes more easier. So when I convert this equation into this standard form, you can see that the j omega by 2, j omega by 10, so the gain modifies. Most important is the gain. So you are able to find the gain after writing the rest of the terms in the standard form. Now when I keep in standard form, because of 2 and 20, you can have a 10 here, j omega, 1 plus j omega by 2, 1 plus j omega by 10. So once I write this one, I can actually analyze that I have a corner frequency 2, a corner frequency 10, and then a simple pole at the origin, sorry, a 0 at the origin, a simple pole located at 2 corner frequency, a simple pole located at 10 corner frequency. So this is the understanding. So I am able to actually write omega equal to 2 equal to 10, the corner frequency, and also a 0 at the origin. That's perfect. Next, I can also express this transfer function in the form of magnitude and phase plot. So once I write in the form of magnitude, each term we're going to express in the sum of log terms. So 20 log 10 plus 20 log j omega minus 20 log 1 plus j omega by 2 minus 20 log 1 plus j omega by 10. One thing we can understand from the simple logarithmic expression is this is a slope. So this is a positive slope, negative slope, negative slope. Moreover, this is plus 20 dB per decade, this is minus 20 dB per decade, this is minus 20 dB per decade. So depending on the sign, we're going to have different Bode plots. So the magnitude will tell us whether the slope is positive or negative. Next, what we're going to do is we're going to sketch each term like this one term separately, this one term separately, this one term separately, this one term separately. So we're going to use all these terms separately, and then we're going to actually draw the Bode plots by adding all the terms. So each term, this one, this one, this one, this one, all 4 terms. We have 4 components, very important, number 1, number 2, number 3, number 4. So, use all these 4 components, we are going to have 4 components in the Bode plot. That is for magnitude. Phase is simple, 10 does not have any phase. So, j omega is 90 degree, 1 plus j omega by 2 is tan inverse omega by 2, because they are poles, you have minus sign, minus sign. So, we can use this information to actually draw a Bode plot. Now, first is to actually locate the poles and zeros. I have 2 corner frequencies, one is 2 and the other is 10 here. So, I am going to place 2 and 10 for example. Before going that, I want to actually forgot to mention of how to actually prepare the Bode plot. So, first in many Bode plots you have this scenario, and then what we are going to do is select the scale. So, if you see the scale here, I select 0.1, the first one, the second one is 1, the third one is 10, 10 power 0. So, this is 10 power minus 1, 10 power 0, 10 power 1, 10 power 2, 10 power 3, 10 power 4, 10 power 5. So, in one Bode plot, if you see, I can start from 0.1 hertz and then I can actually go until 100,000. So, most important, from 0.1 hertz to 100,000. So, this is how my frequency scale. So, students can choose, can start at 0.1, 10 power 0, 10 power 1, any value, but your choice should depend on the transfer function. So, transfer function can have different location of the poles. So, when you have poles at 0.01, better to start at 0.001. So, in our case, our poles are 2 and 10. So, since our poles are 2 and 10, since my pole is 2 and my pole is 10, I actually locate the at 2 and 1 at 10. You see, this is 1, right. So, this will be 2. So, we locate the pole at 2. What is 2? This is 1. So, the next value will be 2. This is 3, 4, 5. So, if you want, you can write 3, 4, 5, 6. Then here will be 100, 20, 30, 40, 100, 200, 300, 400, will be 2000, 3000 and so on. So, 10,000, 20,000, 30,000. So, this is how the Bode plot forms, and this will be 0.2, 0.3. Now, this is the x axis. The next one is the y axis. So, if you are seeing a y axis, I select 0 at this point. You can select 0 anywhere, but it is better to select at the center, because Bode plot has more poles than zeros. So, more poles means more negative slope. So, it's generally to have better, more negative slope. So, you can have 0 here or here or here, anywhere. Now, you can choose the y axis scale 0, 20, 40, 60 or 10, 20, 30, 40. You can also choose 10, 20, 30, 40 and so on. There is nothing wrong. You can always select any scale 5, 10, because it is a linear scale. You can select any values. You can select either unit for 5 dB, 10 dB, 15 dB, it is okay. But just for simple exposition, I actually select 0, 20, 40, 60 dB. So, let us get back. So, coming to here, now I have 2 corner frequencies, one is 2, one is 10. So, I place a pole, like I just draw a line, cross for me represents a pole, I just mark them, 1 or 2 because this is 2 and this is 10. So, at corner frequencies, mark the poles, and then I have a simple pole, sorry, 0 at the origin. I have a 0 at the origin. So, 0 at the origin passes through omega equal to 1 with positive 20 dB slope. So, just mark also this point. So, I also mark this point. Now, let us start with the constant. So what is our constant? The gain is k is equal to 10. K is equal to 10, the expression will be 20 log 10 to the base 10 will be 20 dB. So 20 log 10, I can get 20 dB. So draw a 20 dB line. So drawing a 20 dB line is very simple. I am going to draw a 20 dB line here. So I draw a 20 dB line. So drawing a 20 dB line, it's like a for the constant part for the gain. Next one is always select the pole at the origin or 0 at the origin. I have a 0 at the origin. 0 at the origin gives me 20 dB slope and passes through omega equal to 1. So at omega equal to 1, its dB is 0 dB, but it has a 20 dB increase per decade. So if this is the point, the next point, let's choose a different color. So if this point is 0, in 1 decade it should go by 20 dB. So this is 1 decade. So 1 decade, and see this y-axis, this is 20 dB. So the y-axis is 20 dB. So the x-axis is 1 decade. So because if you see this region, this is decade, right? For 1 decade, it actually goes from 0 to 20. So I am going to draw a straight line over these locations. So I can draw a simple straight line. So it's not very accurate, but I can just draw a straight line over this. So this is plus 20 dB. That is for 0 at the origin. Next I have two simple poles. Two simple poles I marked. So what is for a simple pole? Simple pole has 0 dB until the corner frequency and minus 20 dB from the corner frequency. So it has 0 dB, that's fine. So what I am going to do is it has a 0 dB until here, and from until the corner frequency 2, from 0 dB it going to have minus 20 dB. So when 2 is the starting point, the decade will be 2 to 20. So this is 2, where is 20? This is 10, the next point is 20. So in 20, in 1 decade, it should drop by 20 dB. So the slope should change by 20 dB. So if you see here, this is 2, this is 20. So I am going to connect a line from 2 to 20. So I connect a line 2 to 20. So I use yellow, I use a different color, not many colors here. Let's use green. So that is from corner frequency 2 to 20, very important. Next I have a pole at 10. So 1 decade will be 10 to 100. So if I choose 10, then you should choose 100. So this is the 1 point. So anyway, it also has 0 dB until this point, and then minus 20 dB slope. So minus 20 dB is down slope. So you can actually connect these two and draw a straight line. So now I draw these two lines. Now I actually draw almost all the lines. The question is now summing all these things. So summing all these things is quite easy. So when you are summing any two things, always go to the extreme part of the scale, the location of the scale. So here you see, start here. So you have a line here that is plus 20 dB line, and this one starts at minus 20 dB. So if you sum these two, the curve is going to start at 0 dB with a 20 dB. So 0 dB, so the curve just moves up by 10 dB. But this curve moves until 1 point. So this is the green, I think I better choose a different color. So this curve comes until 2. You see, these two actually contribute to the Bode plot until 2, but after 2 we have another negative slope. So here I have a plus 20 dB slope. So this is plus 20 dB slope, and then from 2, from frequency 2, I have a minus 20 dB slope, and this is also minus 20 dB slope. So minus 20, minus 20. So sorry, this is minus 20 dB slope, and this is minus 20 dB slope, and this is plus 20 dB slope. So the plus 20 dB slope and the minus 20 dB slope will actually give you 0 dB. So we're going to have maintain the same thing until the next point. The next point is the pole at 10. The pole at 10 has minus 20 dB. So this is 0 dB. So plus 20 dB, 0 dB, and then when you sum together the pole, this pole, which is minus 20 dB, it will give you minus 20 dB. So from this point, draw a parallel line with minus 20 dB. So you can have this curve. So when you actually combine all together, we have the Bode plot. So this forms the Bode plot. So this red line, we can actually say this is the Bode plot of our of this transfer function. So if we are try to repeat, we just start with every element and try to draw for each and every pole and 0. Now I just would like to show in terms of simple animation. So for the first constant, it's 10 log 20 log to the base 10, 20 log to the base 10, 10. So it gives you 20 dB. So I get a constant line. So then the next for the j omega, it's a pole. It's a 0 at the origin. So you have a positive 20 dB line passing through omega equal to 1 at 0. So it passes through omega equal to 1 at 0 dB. That's for this one. The next point, we have two simple poles. The two simple poles have corner frequency 2 and 10. So we mark 2 and 10, and then we're going to draw asymptotes. They are like minus 20 dB from the pole. So the simple pole has 0 dB. It has 0 dB. It has 0 dB until this point, and then from here it's going to have minus 20 dB. So this is plus 20. So this will have minus 20 dB slope, and then the next pole also has minus 20 dB slope. Now we have all the 4 asymptotes. It's like adding all these things. So when I add together, I get this nice Bode plot. So this one is what we call magnitude plot. And similarly, for any other system, we can also have a phase plot. So if we actually go through, there is another simple another figure that is clearly shown with all the markings. So you can actually try to understand from here. Now the pole one, sorry, for the phase plot. The phase plot also is similar. So we break it into 3 parts from the phase equation. The first one is 90 degrees. So 90 degrees is a standard straight line. And then you have 2 poles, that is corner frequency 2 and 10. So we place the corner frequency 2, corner frequency 10. So if it's corner frequency 2, you have to select 1 decade before, 1 decade after. So 1 decade before is 0.2, 1 decade after 2 is 20. So choose 2 and 20. From 0.2 to 20, it should be 0 to 90 degrees. You see, this is 0, 90, 0, 90. So for a phase plot, we just only choose 0, 45 degrees, just for scale, and minus 45. So we don't need many scales here. We use 0, 45, 90. Because for the phase plot, its variation is from 0 to minus 90. So 0 to minus 90. You see this? So from 0.2 to 20, because it is 2. If it is 10, 1 to 100. So, choose 1 for 10 and the other point 100. So, you just from 0 to minus 90. So, then once we draw all this one, we can actually combine all this one. So, when you draw a phase plot, it can be bit approximate. So, you do not need to worry because the curves depends on various factors. So, you can't really draw a nice curve is okay, but if you plot all these things, you can actually draw this one. So, you can combine all these parts and you can actually develop a nice Bode plot for the phase. So, this is simple way of for drawing a Bode phase and magnitude plots. If you just remember the basic phase and basic Bode plots for poles and zeros combination, you will be able to draw Bode plot for any transfer function. Next, we have another expression, another transfer function, a simple example where we have two poles and 1 0. Sorry, we have 3 poles, 1 0. So, we can formulate into the standard form. So, you get 0.4 1 plus j omega by 10 j omega into 1 plus j omega by 5. So, we write in the standard form and then we actually identify the corner frequencies, most important corner frequencies, find the corner frequencies. Then we can actually sketch the response. So, if you see here, I actually gave a simple example. So, if you see here, we have pole at the origin and 2 poles at 5. So, 2 poles at 5. So, this is 1, 2, 3, 4, 5 and then you have a 0 at 10. So, I mark a 0 at 10, 2 poles here at 5 and then a pole at the origin. Pole at the origin passes through omega equal to 1, just mark this point. And then we have the x axis already defined. So, y axis I can choose 0 plus 20 dB plus 30, sorry plus 40 plus 60 plus 80 and so on. So, minus 20, minus 40, minus 60. So, if you actually analyze the constant part 20 log to the base 10 0.4. So, 20 log 0.4 actually will give you what value? So, it gives you minus 6 dB because the value will give you minus 6 dB. So, we can actually directly plot this is a minus 6 dB. So, this one is sorry it is minus 8 dB I guess, minus 8 dB. So, we plot this scale because it is minus 8 dB, you can draw a simple straight line. Next, I have a pole at the origin. So, pole at the origin will give you minus 20 dB slope. So, minus 20 dB slope passing through omega equal to 1. So, I am going to use dotted line and actually draw this one. So, this is something like this. So, you have a minus 20 dB line passing through omega equal to 1. Then I have 2 poles at 5, 2 poles at 5, 1 pole minus 20 dB, 2 poles minus 40 dB. So, this 1 pole is at 5, the 2 poles are at 5. So, one decade will be 5 to 50, 20, 30, 40, 50. So, mark the 50 here. In 1 dB, in 1 decade it should drop by 40 dB. So, this this is 20 dB, minus 20 dB, this will be minus 20 dB. So, this one is minus 40 dB. So, if you draw this one, let me use a different color. So, it is going to have a minus 40 dB slope passing through like. So, this is minus 40 dB, this is minus 20 dB and this is minus 40 dB. So, having minus 20 minus 40 and then we have a 0 at omega equal to 10. So, this is a 0, zeros have positive slope. Anyway, all these poles have 0 dB until the corner frequency. From corner frequency, you're going to have plus 20 dB. So having a plus 20 dB, I can actually find, because it's at 0, I can simply draw a straight line with plus 20 dB slope. So I draw another straight line with plus 20 dB. Now I draw everything. We just need to add them. So when you add them, what happens is, when you are adding, start at the choosing point. This is start plus 20, and then this is minus 8. This is minus 8 dB. So it drops by 12 dB. So it drops by 12 dB, and actually it will have. So from 20 dB, you can just select a parallel line to this one, and then we have from 12 dB, these things will have a constant minus 20 dB until 5. So once we draw until 5, this is minus 20 dB, and then what happens is, at 5 you have minus 40 dB, minus 20 dB, and then you have minus 40 dB, so minus 60 dB. So minus 60 dB is, so this value, you have to check this value, this is like 24. So in 1 decade it should change to 84, because this is 24. So where is 84? 60, and this is minus 80. 84 will be this value. So at 50, because you have to choose 50. 5 to 50 is 1 decade, right? 5 to 50 is 1 decade. So choose this value and then draw the Bode plot. So I get this value. Next, the question is, at fifth, sorry, anyway, I think I made a slight mistake here. So although we select the decade, we have a 0 at 10. So although I draw this one, the correct value will be, we have to correct from 10. So I will draw again. So we now identify that it is at 84. So 84 at 50. So what we're going to do is choose this value, but then don't draw. So stop at omega equal to 10. So at omega equal to 10, we have a 0. So this is minus 60 dB, and this is plus 20 dB. 60 plus 2 minus 60 plus 20 is minus 40 dB. So change this one to minus 40 dB. So from here to this one will be minus 40 dB. So this one is minus 40 dB. So just draw another line connecting these 2 points. So this gives us Bode plot. This is the final Bode plot for the magnitude for this transfer function. So it's all about drawing the individual components and then summing them. So if you go back, I gave you another figure with all the components, so you can really understand the poles and 0 locations and then try to draw this one. So these values, if you actually, I think there is a slight mistake here. The locations of these are supposed to be at 5 and 10 rather than. So based on that, we can actually draw these Bode plots, and actually you can actually, for the phase as well, you can actually draw the individual phase components and sum together. So with this one, the students will be able to draw the Bode plots for phase and both the magnitude and phase plots. So with this one, I would like to end this lecture. This is the end of week 14 part 1. In the next part, we shall continue with the Bode plots for quadratic poles. When you have a quadratic poles, the properties are slightly different because we come across eta. So thank you. Kamsahamnida.